Hello, my name is Robert Underwood. I'm a PhD candidate at Clemson University, and today I'm going to be presenting on FRaZ, a generic high-fidelity fixed-rate lossy compression framework for scientific floating point data. This is work that I did while I was at Argonne National Lab in collaboration with Dr. Shang Di and Dr. Frank Capello, as well as one of my advisors at Clemson, Dr. John C. Calhoun. If you have any questions, feel free to email me at robertu@g.clemson.edu. The code will be made available on GitHub shortly after, so please feel free to reach out with any questions that you may have. I want to begin by talking about why do we need fixed ratio lossy compression. Fixed ratio lossy compression is fundamentally designed to address three major concerns. One, large scientific applications produce huge amounts of data. However, the machines that these applications are run on often limit the amount of storage available per project. So for example, on the Oak Ridge Summit system, they limit projects by default to 50 terabytes per project. Many scientific codes such as HACK or CSM produce hundreds of terabytes, if not petabytes of data. So given the limit of 50 terabytes per project for some applications, that really can be quite limiting. So in such a situation, scientists need to be able to reduce their data such that it fits within their budgeted amount of storage that they have. Second of all, they may want to achieve best fit compression. So the users have a certain amount of storage that they have in mind, and they want to compress the data as much as they can subject to their available storage. Without fixed ratio compression, this is actually quite a tedious process. And we'll talk a little bit more in a moment as to why. But typically you either suffer from a loss of quality or you end up doing a lot of trial and error. This is because a lot of the existing compressors that do compression for scientific applications don't really have the concept of a fixed ratio mode. Or they have something similar called a fixed rate mode, and fixed rate modes are not typically, at least as they've been implemented thus far, are not error bounded, meaning that you have a pretty substantial loss in quality. Another major consideration for fixed ratio lossy compression are streaming applications, such as the Advanced Photon Source, the APS, and the LCLS2, which is a particle accelerator at SLAC, the Stanford Linear Accelerator Center. And these instruments send image data out of their main processing systems at a very, very high rate of speed, and it needs to be transported into some sort of analysis cluster, usually located nearby, to make some initial decisions about the data. However, the bandwidth between these systems is actually much more limited than the ability that we have to capture data off of these systems. So compression becomes really important in being able to deal with this incredibly large amount of streaming data. So why is this a difficult problem, or why can't we just use binary search? So first of all, current compressors don't implement fixed rate compression, or they implement the similar fixed ratio compression, which isn't error bounded. For a further discussion of what the difference is between fixed rate versus fixed ratio, please see the paper. In short, one is preserving error over the entirety of the data set, whereas the other is preserving error over smaller subsets of the data set. As you can see, though, in the figure to the right, the relationship between an error bound and the compression ratio is not necessarily monotonic and is often non-convex for different compressors and different data sets. This means that the process of doing this by hand is tedious and perhaps error-prone. And it means that we can't use techniques like binary search because the search space isn't monotonic. So this kind of behavior is true of several compressors, but especially those like SZ, which have a dictionary encoding stage. Anything that resembles like a traditional lossless compressor that does some sort of pattern recognition. So compressors that feature this kind of property can end up with these spikes in the compression ratio. Another question that people have is, why can't we just use a white box approach where we use deep knowledge about the compressor to very accurately model what the compression ratio is? Well, for some compressors that's possible. For some compressors, we just get a egregiously high upper bound that's not really low enough to be useful for commonly seen data sets, or the information quickly falls out of date. So this is a very hard problem, and one that we think can be approached with our techniques. So what are our contributions? We formulated fixed ratio compression as an optimization problem in a way that converges relatively quickly. We illustrate we also evaluated several different optimization algorithms to find one that both A, finds a solution for all test cases that we ran, and then B, modified its performance within our system. And then finally, we implemented and ran a parallel search to improve the overall throughput of this technique. On the right, you can see a depiction of the system that we developed over the course of this project. So at the top, we see a number of users that we have. These are going to be different applications that users are bringing to us. Hack, Hurricane, Exalt, CESM, these are all data sets we tested on. We contributed the design of the system, which we call FRaZ, as well as a number of the components of that system. FRaZ Parallel Orchestrator, which is responsible for parallelizing and spreading the job across a cluster. The Optimizing Auto Tuner, which is responsible for determining the specific air bounds. And then finally, we also developed libpressio, which we won't talk about much in this work, but is a generic abstraction for the compression of dense tensors. So now let's talk about formulating fixed ratio compression as an optimization problem. So first, we're going to consider several things. So in any compression problem, we have some original data set, and in any lossily compressed problem, we additionally have some decompressed data set, D prime. These data sets are parameterized in that they have many fields F and many time steps T. Additionally, the compressors can have fixed parameters, things such as like a mode or maybe a number of quantization bins if they use quantization. We'll call collectively these parameters theta. We have some acceptable compressor air bound. So this represents maybe an upper bound for how much air the users are willing to tolerate in their application. This gives us a function, rho r, which is the real compression ratio. It takes a data set, an air bound, and some fixed compression parameters. And then we also have a target compression ratio, which is based off of the data set. Ultimately, we want to find a target compression ratio which is within a certain tolerance of what the target is. We'll call that target epsilon. Finally, we'll let the air bound of the compressor be E. So if we want to optimize this, or turn this into an optimization problem, we can simply look at the squared difference between rho r and rho t for a given data set, air bound, and parameters, and minimize over E between the range of 0 and the upper bound. With this design, we can determine if something is within our tolerance. If the squared difference is less than the air bound tolerance squared times the target compression ratio, and we can terminate early. So this gives us some performance optimizations we can look at in a minute. Now, the problem with this particular formulation is that many existing algorithms for optimization perform poorly on this particular problem. This is for a couple of reasons. One, we don't have analytical forms for rho r, the derivative of rho r, or the gradient of rho r, or the Hessian for rho r. Since we don't have these partial derivatives, a lot of algorithms use these derivatives to make decisions about what area of the search space to consider next, making this a difficult problem to solve. Additionally, for this problem, computing numerical derivatives can be very costly. Because we don't have an analytical form for even rho r, computing derivative requires us to actually execute the compressor. And depending on what compressor it is, this can take order of seconds to order of minutes. So then if we're imagining computing a numerical derivative, we can compute an inaccurate one, but that would take at least 2 invocations of the compressor, taking order of seconds to order of minutes per invocation. And then additionally, as we saw on a previous slide, rho r is often non-convex and has many local optima. So these local optima make this problem really difficult. So to the right, we've illustrated kind of a cartoon which shows some of the different values of consideration. So we see rho r, which represents the real compression ratio for several different air bounds E. And we have it viewed from both what we'll call the real domain. This is the domain of the actual compression ratios. We have the target objective, and we have some acceptable region, which is basically the objective times 1 plus epsilon and times 1 minus epsilon. So then if we transfer this to the optimization domain, we see that we have something that we can actually guarantee has a minimum near our objective, and we can solve for the particular value that we're looking for. We looked at a variety of different algorithms that potentially could work for this particular problem. Ultimately, we settled on one from a library called dlib, called find global min, which uses a combination of Lipschitz optimization and the NUOA algorithm. If you're interested in the details of this algorithm, I recommend that you review the blog post that we've linked here, written by the author of dlib, which goes into the details of exactly how this algorithm works. So now that we have the search process formulated as an optimization problem, we needed to talk about how to parallelize this process to get the most performance that we can on modern supercomputing machines. So first we're going to parallelize by field. That's really easy. It's an embarrassingly parallel problem. We can compress each field because there aren't necessarily going to be relationships between adjacent fields that we can exploit to improve our performance. However, for time steps, there is often a correlation between the error configuration that works for one time step and the error configuration that works for a subsequent time step. So what we can do is we can treat the first time step as normal, perform a full training operation, and then after we have kind of the first solution, we'll guess that that solution works for the next time step. If that works, then we don't have to perform an additional tuning operation. We can go on to the next time step and just keep doing this until we find out that our solution is wrong, in which case we retune again. We'll talk about how many times that happens, but when we find what kind of a good case for our algorithm, it typically retunes somewhere between 2 and 5 times across the lifetime of the algorithm. Finally, we parallelize by error-bound range. So we're going to split the search range that the user has given us from 0 to u inclusive into n similarly sized subranges, and we run an independent search as hardware allows. So if we have n processors, we'll run them all at once. If we have some number of processors smaller than n, then we'll run them as the hardware becomes available. From our experience, a slight overlap between these regions, approximately 10% of the width of the regions, substantially improves the performance, allowing for essentially additional stationary points that the algorithm can use for finding the trend of the compressor error bound to compressor compression ratio relationship more clearly near the boundaries. So here we have the algorithm kind of illustrated. Basically, we generate a bunch of tasks, and then while the tasks aren't finished, we keep on receiving tasks as they are scheduled. If we ever find a solution that's within our error-bound tolerance, we go ahead and say that we're finished. We cancel all tasks that have not started, and then we wait. And then as we review the list of tasks at the end, we take the one that had the best compression ratio if it was finished. and return that information to the user. So here we summarize the time to solution for the algorithm. And what we see here is that the runtime depends substantially on whether or not the target compression ratio is feasible. So what do we mean by that? So basically, if you ask, in the earlier slides, we saw a cartoon which illustrated kind of a stair-stepping behavior between the air-bound and the compression ratio that we were able to achieve, the real compression ratio. And in the case that we're in a good case, we can actually terminate early most of the time because we find a solution to the problem very early. That allows us to terminate early and we get fast run times. However, we also have bad or infeasible cases. So in the infeasible case, we're going to spend almost all of our time searching, but we're never going to converge to something that's close to the target that the user has asked for. So we can see this illustrated in the two figures at the top. In the good convergence case, we kind of alternate between a real objective which is feasible, which is maybe too high, and then a real compression ratio which is too low, but we never really stay at the compression ratios for our objective most of the time. Whereas for the good convergence case, most of our points are going to be within the feasible region or the acceptable region, and we can terminate early. Some other kind of interesting things that we found is that very small compression ratios often result in infeasible requests. And this is because a lot of compressors have this notion of a minimum compressed size. In the FRaZ air-bounded lossy compressor, this takes the form of the dictionary encoding that they perform as their last stage. And essentially, the dictionary encoding is going to encode things to a minimum size. So if anything is smaller than that minimum size, we're just not going to be able to achieve that compression ratio no matter how hard the user asks for it. Additionally, we see that there are often gaps between what is feasible and infeasible. So in the figure here, if you look at the range between 14 and 16 with high run times, that corresponds to times when we're often in the bad case, where we're often requesting compression ratios that we can't get out of the particular data set with the particular compressor that we're using. So overall, how much time does this take? So you can see at the bottom of the figure that shows the different target compression ratio times. We see this golden region. That represents the amount of time that would be required if we took exactly the correct air bound on our first guess every single time. That's not particularly realistic, but represents perhaps a lower bound for the amount of time that we might be able to achieve. And what we see here is relative to that lower bound, we're often around 2x what the compression time is in the feasible set of cases. Not all the time, but most of the time that is true. Now we also want to talk briefly about the quality of the solution. So fixed ratio, FRaZ and ZFP are generally better than ZFP's fixed rate mode. Remember, fixed rate is the alternative method for achieving a particular compressed size that is not error bounded. And what we find is that we have a higher rate distortion, or a better rate distortion as shown in the figure 1 on this slide, as well as a higher SSIM, a higher PSNR, and a higher visual quality, which you can see in figure 2. So in conclusion, fixed ratio compression is better than the existing fixed rate methods at preserving data quality for equivalent compression ratios. Fixed ratio compression has higher performance when there are a large number of feasible compression ratios. So in other words, when there are many feasible compression ratios, the runtime of the algorithm is going to be smaller, as we can find them typically more quickly. And then finally, we have relatively low overhead in the feasible case of approximately 2 times what it would be if we just jumped correctly to the correct air bound without having to do any tuning. As future work, we identify a number of key points. 1, we want to look at arbitrary user air bounds. So this is the notion that scientists have analysis scripts that they want to run on their data, and they want to ensure that those analysis scripts give the same results with and without lossy compression. So we would call the correctness of the user's analysis scripts, something of an arbitrary user error bound. Additionally, we'd like to consider an online version of this algorithm, which could be used in situ contexts. For example, the streaming algorithm that we talked about earlier. And then finally, we'd like to look at further algorithm improvements to further improve the convergence rate of our algorithm that will allow us ultimately to make the algorithm more applicable to more people. We acknowledge support from the Department of Energy's Exascale Computing Project, the Department of Energy's SCGSR program, as well as NSF under grants listed here, and Argonne's National Lab Bebop supercomputer for computing resources for this project. Thank you for your time.